So our universe, now we're thinking universe, okay? We were at the quantum level, right? We're talking about this little fluctuation of energy at the quantum level. There's a lot of it. Okay, at the universal level, it turns out that if you take all of the mass we see in our universe obeys the condition of a black hole perfectly. Okay? It's really remarkable. You wouldn't expect that. But it does. Right? So this is the equation, the solution to Einstein field equation. It's called the Schwarzschild solution. And basically, it's 2 times the gravitational constant multiplied by the mass over the speed of light square. When you make this equation with the mass that we see in the universe, right, and you calculate it, you get the exact radius of the observable universe that we can see today, right? So our universe actually obeys the condition of a black hole. But think about it. If the vacuum energy is so incredibly dense and so incredibly dynamic, of course the universe must be a black hole, right? With all this energy in it. But even if you forget about the vacuum energy, just the matter energy in the universe makes it a black hole. So then Elizabeth Rauscher and I wrote scaling law to see if there was a correlation like harmonics. Because think about it, like all of a sudden it's like, oh, wait a minute. The vacuum is actually just dividing in harmonics relationship and is making all the scales, right? So we wrote scaling law to see if there was a relationship between the scales, and sure enough, there was. This is the universe, and this is the Planck. So remember how small the Planck is, right? So this is a huge scale from universe to Planck, and then we plotted the stuff in between, and it fell in the right place, okay? And both the Planck and the universe obeys the Schwarzschild condition. They both obey the condition of a black hole. So the little teeny Planck is a little teeny black hole. And the universe we're in is a very large one. And we're in between. Right? You guys starting to get a sense of where I'm going with this? 20 minutes? Oh! Okay, I'm going to have to warp space-time here. I'm going to need your help. Okay, so, of course, the little atom in the middle there is not thought to be a black hole in current conventional physics. So, like, how is this thing lining up with all these other black holes? These are the middle of galaxies, quasars, and all this stuff. And this little atom there is lining up with all that stuff. So it became clear, but the atom then must be one of those little divisions of the vacuum. But when we calculate the mass of an atom, we don't consider the mass of the vacuum inside that atom, right? So that's what I did. That was one of the papers I wrote, the Schwarzschild proton paper. I got a lot of flack for it, a lot. Okay. And basically, by saying the Schwarzschild proton was, for a technical physicist, clearly I was saying a proton is a black hole because the Schwarzschild solution is a solution to a black hole. So I was saying the black hole proton. And the proton, because I figured out it must be the nuclei of the atom that's the teeny black hole, right? And so I took the I took the volume of a proton, right? How much space there is in a proton, right? And I said, how much vacuum Planck fluctuation can be in this teeny little volume? Because the volume of a proton is 10 to the minus 29 centimeter cube. It's like super small. And so I was thinking, is there enough vacuum fluctuation to even make the proton a black hole? And when I calculated, I was blown away. Because there was 10 to the 55 grams of vacuum fluctuation inside the proton. which just happens to be the mass of all the other protons in the universe in one proton in terms of vacuum fluctuations. Right? The mass of the universe in every proton. And there, it linked with so many ancient traditions and masters that talked about that everything is in everything, and the holographic view just emerged, right? I knew from heuristic analysis that the universe had to be somewhat fractal and holographic, but there, the math came out, right? It's like, so, that was awesome, right? No, it really is all one. It's not just like some concept. But you might say, well, how can all the atoms in the universe be in one? But it's just like this. Think of it that way, is that there's information in that one proton that involves all the other protons in the universe because they're all connected. Like, you can't just isolate one proton from all the other protons. You can't put a box around it. That doesn't exist. There's no box that isolates everything from gravitational field, for instance. You cannot. Right? So think of it this way. It's like a CD, right? You get a CD or a DVD of an orchestra playing music, right? It's not like the violinist and the violin and all the people that are in the orchestra is on the CD, right? They're not on there. They're not in, but the information of the music they're making is in there, right? And it's very compactified because you can encode with little bits on this thing. So the bits of encoding of information in the universe is the Planck bit. And so every point in space is in contact and has the information of all the other points in space in terms of Planck bit of information. You guys follow this? So it was remarkable. And when I calculated how strong two protons that would be mini black holes like that would attract each other, I found that the attraction of those two protons would be exactly what we call the strong force. The force that holds the protons together in the nuclei of the atom, which in standard physics was just thrown in. When we found the protons, they were supposed to repel, right? Because they have the same charge. But actually it was just thrown in to make them stick together, right? And so all of a sudden I'm like, oh man, this is a classical solution to the strong force. We can get rid of that. It's actually gravity that's holding the atom together. This would be the source of gravity, actually quantum gravity, what they've been looking for. So I start to dig further. Okay, I start to dig further. I start to think, maybe I gotta start talking really fast. So maybe, what we're seeing when we're looking at an atom is like we're seeing the little, radiation function that's in that region of space localized, but the thing is connected to all the other protons in the universe and we don't know it. And the information transfer of all these protons with all the other protons in the universe is what actually produces the mass that we see as the mass of the proton. You see what I'm saying? And so I'm like thinking, how can I describe that in mathematics? How can I describe that in physics? It's crazy. I gotta somehow find a mathematical formulation that describes the influence of all protons in the universe on one guy. Right? And when I'm done with the calculation, it better come out with the right mass for that one guy. Like the probability of that coming out right was like kind of a long shot, to say the least. Right? You can imagine. So I'm giving you the solution, but this took me 25 years, right? Like, it's like awful. You're thinking, oh my God, this is not possible. I can't calculate that. And then the solution is so simple, it blew my mind. I was like, oh my God, how could I have missed that? Right? How could I have missed that? Never mind, how could 150 years of physicists have missed that? So what I found is this. is that actually, you know, there was already work that was being done in the standard physics community starting to describe that the little plunks on the surface of a black hole actually have a significant influence on the black hole, and that it is the source of its heat. It's called the it's called the holographic principle. And I'm just going to skip slides really quick because we got to get there, because I really want to show you the rest of the stuff. And the holographic principle, basically, they start to describe a bit of information as a little plunk, right? So they were kind of getting on my page, and they started